In this lesson, we'll talk about linear equations in one variable. Before we'll start solving linear equations, let's clarify what's the difference between an expression and an equation. An expression is a sequence of numbers, variables, operation symbols, and grouping symbols. However, the equation works like a balance scale where two expressions are on each side of the scale. So an equation is two expressions connected by an equal sign. We could visualize these two concepts by comparing it to English language. For example, an equation will correspond to a sentence. Something is equal to something, a full sentence. However, an expression is just a phrase. It's not a full sentence. For example, we could say, an interesting problem is just a phrase. To make it an equation, we could say, this problem is interesting. It's quite important that we recognize if we deal with an equation or an expression, because equations can be solved, while expressions can only be simplified or evaluated. For example, here we have an equation. This left-hand side is equal to 0. This equation can be solved. You could guess that if x is -3, then the left-hand side will indeed be equal to 0. So x equal -3 would be a solution to this equation. If x will have different value, the equation will not be true. What if we consider just the left-hand side, if we don't write equals 0 here? Well, this will be just an expression, and such expression can't be solved for anything. It can only be simplified or evaluated if we know the value of x. For example, in this case, we could simplify it by multiplying 1/2 through the bracket using distributive property. So 1/2 times 2x would be just x, and 1/2 times 6 is 3. Okay, so we know that this expression is equivalent to x plus 3. And obviously we could also evaluate this expression. For example, since this is equivalent to x plus 3, it's enough to evaluate x plus 3. If x is 0, then the expression has a value 3. If x is 1, then the expression has a value 4, and so on. Again, in summary, equations can be solved, while expressions can be simplified or evaluated. What's a linear equation? Well, a linear equation in one variable is any equation that can be expressed in the form ax plus b equals 0. And it happens that any equation that involves a variable but only in the first power can be written in the form ax plus b equals 0. So any such equation will be called linear. On the left-hand side, we can have a linear polynomial, and on the right-hand side is just 0. Notice that if a is 0, we deal with the generated equation, just constant b equals 0. So even such equation would be called a linear. Let's see some examples of a linear equation. 2x minus 7 equals 3. Obviously, we could subtract the 3 from the left-hand side, obtaining 2x minus 10 equals 0, and as you see, this is of the form ax plus b equals 0, so yes, it is a linear equation. Another example, this time if we move all the terms to the left-hand side, the 5x will cancel each other, and then we'll end up with -5 equals 0. Well, it's still a linear equation, however, this equation is never true. That just tells us that we don't have any solution for this equation, and perhaps the simplest equation is 1 equals 1. This one is always true. Notice that no matter what x is, the 1 will always be equal to 1. So x can be anything, and the equation will still be true. Therefore, the solution for such equation will be all real numbers. We'll talk about it on the next slide. Now let's look at examples of nonlinear equations. For instance, 8 over x equals 5. Why this is nonlinear equation? Well, because the x is in denominator. We should not keep the variable in the denominator. That will be a rational equation. And another example, here we have root of x. Okay, as you see, this doesn't have a form ax plus b because of the square root. Such equation will be called a radical equation. And finally, here we have a polynomial x squared plus 3x equals a constant. Even if we move this constant to the left, the polynomial on the left-hand side is of the second degree. So it's a quadratic polynomial. It's not linear because of this exponent 2. Okay, so we can't have variable in the denominator, we can't have a root, and we can't have exponent higher than 1. For example, 2 or 3 or any higher one. Okay, since we already know what's a linear equation, remember that's any equation that can be written in the form ax plus b equals 0. Now we would like to solve linear equations. So what does it mean to solve an equation? Well, first of all, we need to know what's a solution. Solution to the equation is a value of the variable that will make the equation true. So the left-hand side should actually be equal to the right-hand side if we replace x by the solution value. Solution set is a set of all possible solutions, because sometimes we have more than one solution. For example, infinitely many solutions. Let's come back to the examples from the last slide and try to solve them. Well, to solve this linear equation, we would like to leave the terms with x on the left-hand side and bring the 3 terms to the right-hand side. So 3 was on the right, let's copy it. However, -7 was on the left. Well, to bring the 7 to the other side, formally we add 7 to both sides of the equation. So when we add 7 on the left, this -7 will be cancelled, and on the right the 7 will be added, so we end up with 2x equals 10. And now it's enough to divide by 2 both sides of the equation, so x would be 10 over 2, which turned out to be 5. Okay, therefore 5 is the solution to this equation. If x is equal to 5 and I plug in the value 5 instead of x, the left-hand side will be equal to the right-hand side. Well, let's check this. 5 times 2 is 10, minus 7, yes, it is 3. So 5 is indeed a solution. Therefore, the solution set to this equation is a one-element set composed of just 5. Let's see the second example. We actually solved this already in the previous slide, but this time let's focus on the solution set. So as before, we can subtract 5x from both sides of the equation, leaving us -1 equals 4. Obviously, -1 is not equal to 4, so this is never true. If the equation is never true, the solution set is actually an empty set. Finally, 1 equals 1 is always true. So what is the solution set? The solution set is actually all real numbers, because no matter what the x is, the 1 will be equal to 1. The equation will be true. If x is 5, 1 equals to 1. If x is 10, 1 equals to 1. If x is 58.5, 1 will be still equal to 1. So such equation will be called identity. And let's summarize our cases. If our linear equation has exactly one solution, such equation is called conditional. Like example A. This is conditional equation. This equation is true under the condition that x is equal to 5. If x is equal to any other value, the equation won't be true. If the linear equation has infinitely many solutions, if all real numbers are the solutions, such equation is called identity, like the last example. That was identity. And finally, if the linear equation has no solutions, such equation is called contradiction, and that was the middle example. The solution set was empty. Okay, therefore any linear equation can be classified as conditional, identity, or a contradiction. Also notice that for a linear equation, you may have only one, infinitely many, or no solutions at all. You can't have, for example, exactly two solutions. Okay, generally, what strategies would we use to solve any linear equation? Well, first of all, to solve an equation really means to change the equation into equivalent forms until we'll get the statement x equals to specific number. So what are those equivalent equations? Those are the equations that will have exactly the same solution sets. So you can change the equation in many different ways, except that the resulting equation must be equivalent, must still have exactly the same solution set. So what are the strategies of changing equations equivalently? Well, we can produce equivalent equations by either adding to both sides of the equation the same value, or multiplying both sides of the equation by the same value. However, this time we need to remember that this has to be a non-zero value. Obviously, we can't multiply by 0 both sides because then we'll end up with always true equations, even though the original one didn't have to be true. Notice that I've been using words like adding and multiplying. I didn't say subtract or divide. However, subtraction is hidden under addition because we're adding a negative number, so that's the same. And division is hidden under multiplication because we could multiply by a reciprocal. So yes, all four operations can be applied to both sides of the equation except for multiplication or division by 0. And let's practice solving some linear equations. Okay, how do we approach this problem? Since we have a bit bigger expressions on each side of the equation, the idea is to simplify those expressions. And to simplify any expression, we just follow order of operations. In order of operations, remember the first thing is to deal with brackets or grouping signs, starting from the most inner ones and working your way out towards the outer ones. So what we're supposed to do here is release this bracket by reversing the signs inside the bracket. So that becomes -3 and positive x. Let's copy the rest as it is. Keep the big bracket. And we'll deal with the square bracket in the next line. On the right hand side, similarly as before, distribute the negatives, switch the signs, so it's -2 and -7x. Now, before we release this square bracket, I would suggest that we first combine like terms. So make the expressions shorter. 2x plus x is 3x, and 5 minus 3 is +2. Okay. Now it's -2, -7x, and it's time to release the square bracket, so multiply through. 4 times 3 is 12x, and 4 times 2 is 8. Copy the right hand side, and now it's time to collect all x's on the left hand side. Therefore, this -7x will travel over this equal sign to the other side, and it will change the sign. So formally, what we do, we are adding 7x to both sides. And also, we would like to move the 8 to the right. So the next operation will be subtracting 8 from both sides. Okay, let's write it down. 12x plus 7x. And here it's -2. The +8 becomes -8. Now let's combine like terms. So we have 19x equals -10. And finally, divide by the leading coefficient, divide by 19, which gives us x equals -10/19 for the final answer. Let's see example B. This time we deal with some fractional expressions. And since working with fractions may not be so pleasant, let's get rid of those denominators. How can we do that? By multiplying by LCD of 5 and 2, which is 10. This would cause that every single fraction will be multiplied by 10. Let's write it gently above here. And we could reduce the 10 with the denominator, leaving just the 2 in the numerator. Here we reduce the 2 with 10, leaving 5. And over there as well, 5. So after clearing those denominators, well, the equation becomes a lot easier. It is 2 times everything what's in the numerator. Let's write it in a bracket. No fractions anymore. And 5 times the old numerator, 3x plus 1. And finally, 5 times negative x plus 7. Now we have nearly the same stage as the example before. So we need to work out through all those brackets. 2 times 2 is 4x plus 2 times 5, distribution rule, right? 2 times 5, 10. 5 times 3, 15x plus 5 times 1 is 5. And then it's minus because it's plus 5 times negative 1, so it's negative 5x. And 5 times 7, 35. Finally, let's collect all x's to the left. So I have 4x as it was. Now this 15x travels over the equal sign to the left, so it becomes negative 15x. Formally, we're subtracting 15x from both sides. But practically, this 15 goes to the other side of the equal sign with opposite sign. Okay, and then the next term, negative 5, when crosses this equal bridge, it becomes positive 5. It changes its sign. Now let's put the equal sign, collect the three terms on the right hand side. 5 plus 35 is 40, and bring the 10 over the equal sign to the other side, so it becomes negative 10. It is like subtracting 10 from both sides. Okay, now we're ready to collect like terms again. So we have 5 minus 15 is negative 10 plus 4 is negative 6x. And over there we have 30. And the last step would be to get rid of the leading coefficient. So we are dividing, because we are changing this multiplication into inverse operation, which is division, but we're still dividing by negative 6. We don't change this negative, because we are not changing subtraction into addition, we are changing multiplication into division by the same coefficient, negative 6. So x becomes 30 over negative 6, which equals negative 5. Final answer. Okay, so you've seen two examples of solving linear equations. Please practice at least 10 more examples from the textbook. And after each example, please check the answer. If anything is wrong, practice more. Okay, let's put together the general guidelines for solving linear equations. So we'll review all those steps that we took to solve the above two examples by looking at, for example, this equation. Here we have an equation that involves some fractional numbers and some grouping signs, brackets. So what do we do first? Well, we like to clear all fractions or decimals, because those fractions could be some decimal numbers. So how do we do that? Well, we multiply by LCDs of the denominators. So the LCD for 6 and 8 is 24, because 24 is divisible by 8 and it's divisible by 6, and it is the smallest number with such properties. So let's divide the whole equation by 24, meaning that each term of this equation, first term, second term, third term, term means cluster of letters, numbers, or expressions in a bracket connected by multiplication. So here's a multiplication, 1/8 times a bracket, so it's one term. Then it's plus, that separates the terms. Then it's 3, single term, and another term because it's connected by multiplication. Okay, each term needs to be multiplied by 24. Let's write this little 24 here so we will remember it. Here and here. I do stress the importance of recognizing those terms, because sometimes students, after multiplying, for example, this big term in the beginning, they may overlook multiplying the 3 by 24. This term also needs to be multiplied. So each term needs to be multiplied exactly once by 24. For example, Another common mistake is multiplying 1/8 by 24 and multiplying the bracket by 24. That will be too much, because if you have a product of two quantities, it's enough to multiply one factor of this product in order for the whole product to be multiplied. So what we do here, we really reduce the 24 with 8 to make it easier and figure out what is it that we actually multiply the bracket by. 24 by 8 is 3. Therefore, this bracket will be multiplied just by 3. Okay, let's see it. 3 times the bracket. The second term will simply multiply. 24 times 3 is 72. And finally, the last term on the right-hand side, again, we can reduce 24 with 6 first. That leaves us with 4. And this 4 will have to be multiplied by 5. So altogether is 20 times the bracket. So that's the process. And please take your time to clear your fractions correctly. This is probably the most important step in solving this kind of equations. After this hard work, the equation will be similar as the one in the 1a example. So the rest of it will be probably easy. But commonly, the most mistakes happens in the first step. So please take your time to clear those fractions correctly. Okay, I also mentioned that such equation may involve, instead of fractions, decimals. If that's the case, what we do, we multiply by appropriate power of 10. Such power that will cause moving the decimal exactly after the dot. So after this step, we will deal with only integers. No fractions and no decimals anymore. Okay, when we are at this stage, the next step would be to release all the brackets. So we multiply through this bracket. 3 times 2 is 6x, then it's -3 plus 72, 20 times 5 is 100, and -3 times 20, -60x. Now, we want to keep our equation always in balance, like a balance scale. So whatever we do to one side, we need to do to the other side. Okay, next step would be to collect and combine variable terms on one side of the equation, usually left, but not necessary, and free numbers on the other side. Just separate the like terms. So the 6x should go with 60x. Formally, if we want to move the 60x to the left, we are adding 60x to both sides. Practically though, the -60x, since it travels over this equal sign to the other side, it becomes positive. Similarly, with the free numbers, we copy the 100, then the -3 goes to the other side of the equal sign and becomes +3, and the +72 goes to the other side, becomes -72. So the formal step is +60x, then it's +3, and it's -72. But I wish that you will keep this in your mind. You don't necessarily have to write this. You just think about shuffling the terms to the other side by switching the sign of the term. So the negative becomes positive, the positive becomes negative, and the negative goes on to positive here. Okay, now it's time to combine like terms. So we're just adding 60x plus 6x is 66x, and 100 plus 3 minus 72 turn out to be 31. The final step is to get rid of this leading coefficient 66, therefore undo the operation of multiplication, which means we're dividing both sides of the equation by 66, and the final answer turned out to be 31 over 66. So this is the step when we isolate the variable by dividing by linear coefficient. That's the leading coefficient 66 that goes to the denominator. So every linear equation, no matter how complicated, can be solved by using those steps. Clear up fractions, work out your brackets from the most inner out, collect terms with the variable on one side and the free terms to the other side by switching the sign when you move the term over the equal sign. And finally divide by the leading coefficient. Always keep the balance within your equation.